Hello and welcome to this episode of Math with Martinez. In this pre-calculus video, we're looking at our third unit, which is all about polynomial and power functions, equations, and inequalities. This episode, we're going to be focusing on skill 1 from this unit, and it is to graph polynomial and power functions and their transformations whenever f of x, that parent function, is replaced by some kind of transformation that's going to be caused for specific values of a, b, c, and d. So ladies and gentlemen, let's begin. Polynomial function graphs. They can be transformed. Remember, we have all of our parent functions. We studied those in our first unit. But from those parent functions, you can see in their family graphs that look like the parent but are a little bit different due to these types of transformations. The first type of transformation, it is a slide or a shift of our function graph. That slide or shift is called a translation. A sliding or a shifting to the left or to the right, or perhaps up and down, that is a translation. Now, when we stretch or compress a function graph, that is called a dilation. It's going to keep the same shape, but it's going to be stretched or pressed down. And last but not least, whenever we flip a function's graph, that is called a reflection. So with these three terms now, let's go ahead and look at the rules. Now that we know some language, let's look at specific rules for polynomial functions. Now the standard form in which the equation of a polynomial function can be written is like so. And I'd like for you all to highlight as I am doing. It is that our function f of x is equal to a. That a value is going to cause some kind of transformation. We'll get to it in just a moment. And then x minus our h value, that is also sometimes denoted different contexts or textbooks or professors. They might use either an h or a b value. They could say, I'm sorry, c value. I said the wrong letter. And then that expression, the x minus h, is raised to the power of n. And then last of all, we have our plus k value out on the end. Sorry, let's use blue for that. And again, some texts will, instead of the k, they'll use the letter d, just so that you're aware there. Where n is the power of our polynomial function. Remember, you can have even power polynomial graphs, or you could have odd power functions, right? That can happen. And now let's talk about what do these values of a, h, and k do to our graph. The vertex is that point hk. That's that key central point, that like turning point, usually where our symmetry line is going to be going through. H is the horizontal translation from the origin, and K is the vertical translation from the origin. Big ideas, and make sure you highlight that. Now, this line of symmetry is determined by our A value. This line of symmetry is determined by our A value. But what I want us to write in here is not just really where our line of symmetry is occurring, but I want us to make a note that the the slope or the rate of change is a better way of saying this. The rate of change of the two lines, or we could say if they're not straight lines, like for an absolute value graph, or we could call them the arms of our graph. That's maybe a better way of thinking about that. The arms of our graph are going to be determined by our A value. If we have this A value, that is going to be, if it is greater than 1 when we take the absolute value, then it's going to be steeper. But if the absolute value of our A is something between 0 and 1, it's going to be compressed. It's going to look smushed down, like from on top and bottom. It'll look like we smushed it. And when the A value is negative, it's going to cause the graph to flip vertically. That is that reflection that happens. So when our A value is negative, the graph flips vertically from that vertex point. And whenever we want to graph one of these functions, it's always a good idea to first plot our vertex and then move from there according to our A value or the rate of change. So let's go ahead and take a moment to look through some of these exercises. We're going to state the transformations of the polynomial functions from their parent function. So in order to state the transformations, we have to know, well, what was the parent function to begin with? This function right here, notice its power is 2. Its power is 2. So what do we call a polynomial function whose power is 2? That is a quadratic function, and the most basic is just x squared. That's the most basic quadratic function. It's the parent function for this now function that has been transformed a couple of ways. Let's take a minute here and identify our vertex. What is our vertex? What are the h and k values? Because the h and k values are going to tell us how it translates and where our vertex is located. All right, so let's think about the h value first. Notice that the h is going to be after the subtraction. It's what we are subtracting from our x value. So what is that? That is going to be 2. It's going to seem opposite. It's going to seem opposite. Notice here, it's not a negative 2, but this h value, h is always opposite in the function form. So when it's written in function form, it looks opposite. It looks like opposite of what is our vertex value. And then our k value, what is that k value going to be? That value that is out on the end, causing a vertical movement. It's going to be a 3. And then last but not least, what is our a value? What is our a value? That is the value in front of our function. In front of our function, what do we have? Just, it looks like a negative. So what is it? It's not just negative, but a negative 1. So we've got our h value, our k value, and our a value. Now, what transformations occur here? Well, because of our h value, because of that h value, which is 2, that's going to be that horizontal movement. It's going to move 2, oops, I'm so sorry. I keep using my highlighter instead of my pen. It's going to move 2 units to the right. That's the first part. Then, because of our k value of 3, that k value is the vertical translation or shifting. It's going to move 3 units up. And then last but not least, because of our a value being a negative 1, because it is negative, it's going to be flipping vertically. It's going to be flipping vertically. Now, it's not going to be stretching because it's not greater than 1. And 1 is not between 0 and 1. So it's only going to be that it flips vertically. We're going to have a vertical reflection. So there you have it. Those are the transformations that occur. And this was really nice and easy to pick out. We didn't even have to use a graphing calculator. We could use it to verify and check that that is the result, that it does in fact look like that. But what I wanted to show you here is, yeah, we can pick it out just from the way that it is written. When it's written in this standard form, we can very quickly pick out those transformations by knowing hk and our a value. Let's do the same for this next function. What is the parent function, the most basic function that this function has been transformed from? Look at the power. This is a power 3. This is a cubic function. And its parent, the most basic cubic function, is just x cubed. So what's going to be our vertex? What's going to be our vertex? Remember, to find your vertex, you need to know your h and your k value. Your h and your k. And remember what we said, our h is always opposite in the function form. What does it look like our h value is here? 3. But it must be opposite, therefore our vertex is in fact a negative 3. What about our k value? What has been added out at the end there? Well, I've highlighted what looks like nothing. What's the number that represents nothing? It is 0. And then don't forget, we need to know our a value. What is our a value? It is 2. That's that value in front of the quantity that is cubed. So with these values, knowing now our vertex and our a value, what transformations happened here? What transformations happened here? Let me take a minute just to show you this graphically. Think about your parent function. What's our parent function? Our parent function is just x to the power of 3. But what is this function now? It's 2x, and then it was plus 3. And all of that is being raised to the power of 3. Let's look at the graph here. Do you see what's happened? Do you see what has happened here? Oh, I'm going to zoom in because this is zoomed out like crazy. Notice on the side there it said like by thousands. Let me just do a quick zoom, and I'm going to choose option 6 because that's the standard window. There, now we can see it more clearly. Okay, we've got, to begin with, the blue function is our parent function. So the blue one is what it is originally. The red one, notice what happened here. It moved which direction? It moved to the left. It moved 3 units to the left. That's because of our h value. There was no k value, so it didn't move up and down at all. But what does also happen here is a little something because of our a value. What does our a value do? When a is greater than 1, then the graph is stretched or a little bit steeper. And you can kind of see that here, that the red graph is a little bit steeper than the blue. It's kind of hard to tell really carefully, but its rate of change is a bit more steep. And so that's what we want to say here, that it is that we have a vertical stretch by a factor of 2. That it is vertically stretched by a factor of 2. And really, a good way to see that is by going to the table. When you look at the table here, you can see that what happens here are values. Oh no, it's kind of hard to see at the table. Never mind. Disregard what I just said. Okay, let's think about example number 3 here. Example number 3. What is the parent function for this graph? This is a power function, power 4, and its most basic, it's just x to the 4th power. Y'all, try it now yourself. What is going to be the vertex of this function? What's the vertex going to be? All right, well, we need to find our h value. It's opposite of what it looks like, so it should be a -6. And then our k value is here at the end. That is a -5. That is our new vertex. And our a value is -3. Now let's use these pieces of information to identify the transformations. Our vertex is no longer at the origin. Our vertex has been moved 6 units to the left. That's that horizontal translation. 5 units down, that's that vertical translation. And now, because this is a -3 for our a value, there's 2 things that happen here. Because it is negative, it's going to be reflected. It's going to be reflected vertically. We have a vertical reflection. And not only that, but because it is a 3 and the absolute value of -3, the absolute value of -3 falls into this category, greater than 1, it is going to be quite a bit steeper. So it is stretched by a factor of 3. So it's reflected vertically and stretched. By a factor of 3. Cool. Okay, you guys, last one. For this example, what is the parent function going to be? All right, it is a power function, power of 5, and the basic would just be x to the 5th power. We've got a lot of changes here. What is the vertex for this function? The vertex is 5, 4. Make sure that you take the opposite of the h value of what it looks like in the function's form, and then your k value. Now, what does that mean for the transformations? We'll get to our a value in just a moment, but what does this h and k value imply for the transformations of this function? It's going to move 5 units to the right. And 4 units up. Now, let's talk about the a value. a value is pretty clearly 1/2. But what is that going to do? Go back to the previous page with me. 1/2 for an a value, when we take the absolute value of it, is going to be this value between 0 and 1. That's an a value between 0 and 1 when you take the absolute value of it. That's going to cause a compression. So our graph is going to be not as steep. So let's go ahead and say that in here. And compressed. Compressed how? Vertically. By a factor of 1/2. So there you have it, ladies and gentlemen. That is our introduction to polynomial function graphs and their transformations. How do we find those transformations? We've got to look carefully at the way that it is written. If it's in standard form, we can pick out our a, h, and k. That h and k are telling us the translation of our vertex. And our a is telling us if those arms have been stretched or compressed. Also, that a tells us if our graph flips. That is it. If you all had any questions while watching this video, will you take a moment and share those now? And until next time, stay fired up.